Hello everyone, this is Professor Kuehn, and welcome back to my lectures on electricity, magnetism, and light. We have been looking at the work of Christiaan Huygens and his treatise on light. We've gotten up to about chapter 15 in A Student's Guide to the Great Physics Texts, volume 3. In chapter 15, what Huygens does is explains how his wave theory of light can account for the law of reflection. Before we start into chapter 15, let me remind you of where we have been. So one of the central features of Huygens' theory of light is what is now called Huygens Principle. So let me remind you what Huygens Principle states. And he doesn't call it Huygens Principle. I suppose that might be a bit arrogant if he did so, but now we call it Huygens Principle. And really there are three elements of Huygens Principle. He says when you're considering waves, he says every point on a wave front is itself the source of spherical wavelets. So little waves spreading from each point on the surface of a wavefront. Secondly, these wavelets mutually interfere. They mutually interfere with one another. So interfere here has a technical meaning. They can experience constructive or destructive interference. More generally, you use the superposition principle to add them up or to sum them. And then the sum of these wavelets forms the wavefront at any later time. At any later time. So if you want to know how a wave is propagating through some region of space at any time, you just take the previous wavefront, break the wavefront into a bunch of little point sources of wavelets, let these propagate forward, sum them all up, and you'll get what the wave looks like at any later time. This kind of procedure, by the way, is extremely useful and is amenable to computer programming if you're wanting to know, for example, how the waves of sound spread through a concert hall, or if you want to know how the waves of an earthquake travel through regions of the Earth. So this is an extremely useful principle that's used today, even though nowadays people don't use the notion of ether, as Huygens believed in it, to understand the propagation of waves. Nonetheless, this principle is an extremely useful principle. So just to make a sketch of what we're talking about here, you might imagine if we have some barrier, we're looking at it from above, and suppose we have some waves, let's say like water waves coming in. I'm drawing these wave fronts coming and striking this barrier. You can consider each point along this wavefront. I know I'm only going to draw 3 or 4 or 5 dots here, but each one of these then can be thought of as a spherical source of waves that sends out waves like this. Unfortunately, I've drawn these to be looking closer together, shorter wavelength than the ones coming in, which they should not be. They should have the same wavelength as the ones coming in, but I think you get the point. So you get this very complicated scenario where you have all these overlapping wavelets, you sum all of those up, and then at any later time you'll find that you get interference between them in such a way that you get a nice wavefront that's tangent to these at a later time. And then you can consider these to be spherical sources, and you can get a new wavefront here, and so on. So this is kind of the strategy for determining what the wavefront at any later time looks like. Now, how does Huygens use this? So the uses that Huygens makes of this is, first of all, he says it explains the rectilinear or straight line propagation. He uses the word rectilinear. I didn't spell that right. Rectilinear. Get rid of this E. Rectilinear propagation of waves through a barrier, through a window, let's say. So remember, one of the puzzles that he's trying to address, this is something he does in chapter 14, is if you have a window and you have sunlight outside, I'll draw some sunlight here, there are waves of sunlight, you might imagine using the wave theory of light that these waves would spread into the entire room through the window. But he says it seems rather from everyday experience when you punch a hole, let's say you have a shade, you punch a hole through it, there's a straight line of light. So I'll draw kind of, maybe I'll make those orange so it doesn't look like they're wavefronts. You have this sort of straight line of light that comes through the window. So how can that be reconciled with this spreading of waves one might anticipate from the wave theory of light? Well, he says you have all these little sources, once again, these cause these spherical waves coming through like this, but the point, he says, is that later on, the waves arriving in this region over here are out of phase with one another, and hence they cancel each other and it's dark in this region. But here the waves add together nicely, and so it is bright in this region. And sure, there's a little bit of spreading, but generally speaking, the wave will travel in pretty much a straight line. So you get a beam of light just like we are used to from light going through a hole in the wall or a hole in a window shade, for example. Now, as I mentioned before, one of the things he did not anticipate, at least in this text, is that in this region where he said it's completely dark, by the way, this is in chapter 14, I'm just reviewing this, in this region where he says it's completely dark, you do actually have regions of, there are regions of constructive interference in these regions that he did not anticipate, in these dark regions. Okay, and that's the analysis that we talked about in number 2 when we talked about the diffraction of waves through an opening, such as the window we showed above. And we talked about in that explanation in class how, if you have this barrier, you break this up into a whole bunch of little point sources, and then you look at a screen over here, and you'll find that you will have some regions where it's bright, a bright region in the middle. So here I'm trying to draw the intensity or the brightness of the light landing on this barrier over here. And you'll have this central bright region. That's what he's talking about right up here. But then you will have a dark region, but then you'll have these other bright regions off to the side, dark, bright, dark, and so on. These are called these interference maxima and minima that arise from the wavelets coming from each of these point sources, constructively and destructively interfering at various angular separations from the central bright fringe. And this phenomenon is called diffraction. And the formula that tells us where the dark spots are, if this is a width A right here, let me just make this in red, that's width A. There's a formula A sine theta sub n equals n lambda. This would be the locations of the diffraction minima, or in other words, the dark fringes. And we talked about how one arrives at this formula. Okay? So there are bright and dark fringes off to the side, so light doesn't travel strictly in a straight line. You get these other things, but they're very dim fringes. And the important thing to note is that as you make, counterintuitively, as you make this slit narrower, you make A smaller and smaller, the angular locations, theta n, of these peaks spread out more and more. So if I were to draw the angular locations of these diffraction minima, so this right here would be theta 1, the angular location of the first minimum. This right here would be theta 2, the location of the second diffraction minimum. As you make A smaller and smaller, those angles get larger and larger, so there's actually more spreading of the wave when you have a narrower and narrower slit. Okay? And then finally, one of the things that I alluded to was looking ahead when we talk about the Young two-slit experiment, looking ahead at Thomas Young's 1809 two-slit experiment. And I haven't demonstrated this yet, I'm just going to tell you. When you have two slits in a barrier, but these slits can be taken to be extremely thin themselves, and you look at this, a screen over here, you once again will get these interference maxima and minima like this, a central bright one, and then fringes off to the side. In that case, you will get a formula that looks very similar to this. If D is the spacing between these slits, you'll get a formula that looks like D sine theta n equals n lambda. But, and this is important, the formula here, this is the location of the interference maxima. And again, I haven't demonstrated this to you here, I'm just telling you what it is. So this would be theta 1 in this formula, when you have two slits, would be the location of the first interference maximum. Theta 2 would be the location of the second interference maximum. Okay, so you don't want to confuse a single slit diffraction formula with the two slit, the single slit diffraction formula with the double slit interference formula. Okay, so tell you what, this is all by way of review of what we've done in the past week or so. What I want to do now is I want to go on in chapter 15, where Huygens talks about reflection of light waves. He's going to use Huygens' principle to explain the law of reflection from a mirror surface. And this is figure 15.1. And tell you what, why don't we take a break here and I'll pick this up in my next lecture.